So when we're talking about finding extrema, there's basically two different scenarios that we would approach. Like we would either be finding local extrema, and for that kind of thing, we would use the second derivative test in order to classify whether something's a local min or max or a saddle point. And if we want to find global extrema, it's going to be much the same situation as it was in the one-dimensional case, where we're going to check all of the critical points as possible candidates, and then we're also going to check the endpoints. Now, the trickier part here is going to be those endpoints, right? Because on a single variable function, so just say something like f of x equals x squared on -2 to 2, for example. Right, so just as a reminder of how we did these problems. Okay, so this would look something like this. Right, so we would find our critical points, which in this case would just be 0. And that's one candidate for the absolute max or min. And then we would also check the endpoints, right? So here we would get the absolute min being at 0, and the absolute max would actually be a tie here at both 2 and -2. But those are the possible candidates. Now, with the nature of how our domain is one-dimensional, meaning it's only on the x-axis, right? It's just this number line of points. There's only a possibility of 2 endpoints. But as we've seen in exploring these multivariable functions, the domain for a three-dimensional function, meaning 2 independent variables, 1 dependent variable, is much more complicated, right? Our domain is 2-dimensional now instead of 1-dimensional. It has both those x and y points. So that opens up really an infinite number of points on the boundaries. So we have to figure out ways to test all of those points. And this is where drawing the domains of the functions can be really handy. Not essential, like you can do it just algebraically, of course, but I think that it really helps you see exactly what's going on. So first, let's just go ahead and set up some theorems that we're going to use in finding these. So first up, we're going to need the extreme value theorem. Okay, and we had a version of this with single variable functions. So this is just going to be the analogous version for multivariable functions. So this says that a continuous function f defined on a closed bounded set attains an absolute maximum and absolute minimum value at some point in the set. Okay, so we've expanded the definition away from a closed interval, a closed bounded interval, to a closed bounded set, right? So if you remember the extreme value theorem, in one variable would be some closed bounded interval, which would look like this, where a and b are both finite numbers, right? That's the bounded part. The closed part is that you have the closed brackets here, meaning you include the endpoints. So now a closed bounded set is going to look a little more complicated. So some examples here, we might have all the x and y such that maybe x is less than or equal to 3 and greater than or equal to 1. And maybe y is the same thing. Okay. So what would this look like exactly? And you've already seen some of this on the homework a little bit, but just as a reminder, so we're looking between 1 and 3 for x, right? So these possible x points, and then we're expanding that out to between 1 and 3 for y, right? So that would be these. And we're kind of looking at where do those regions overlap, right? So the actual region here would be this part right here. Okay. So this would be our boundary, our closed bounded set. So it's closed because it does include the endpoints here. So typically these greater than or equal to, less than or equal to, that's implying that it's closed. It's including those boundaries. It's bounded because, it's clearly not going to infinity or anything like that. Okay, and as I mentioned on the homework, sometimes these are written like this. I think this is more common once we get to like the double integrals and we're looking at integrating over rectangles and stuff like that. In the Stewart textbook specifically, I didn't see it before that chapter denoted like this, but that is a common notation for it. Another example, which is common, maybe we have like a circular region. Okay. And we can really have any region. I'm just looking at ones where, we actually kind of have like a chance at finding these, right? You could have a really complicated region which is closed and bounded, and you might not really have any feasible chance of checking all the points if it's not very easy to work with algebraically. So this one would be a circle, so centered at 0, 0. In general, the equation for a circle looks like this. Okay. The equation looks like this, where r is the radius, AB is the center. So here, with no a and b terms, the center is at 0, 0. The radius is at 1. I'll make this a little bit larger. All right. And because it's less than or equal to 1, it's all the points within the circle. Okay. So this would be a closed bounded region. So something like x squared plus y squared is greater than or equal to 1. That would not be a bounded region, right? That would be like the outside of the circle. So it would be going out to infinity. Something like x squared plus y squared is less than 1. Now it's not a closed region because the boundary is not included anymore. Okay, so these are all things we need to consider when we're approaching the extreme values, the global maxes and mins, and deciding whether or not they're even going to exist in the first place, right? And now it doesn't need to be closed and bounded in order for you to have global maxes or mins. Like for example, the function x squared is, if you just consider the entire function not on a closed set like we did here, it does have a global minimum, right? It's just, it just wouldn't have a global maximum in that case, right? So these are, it's like if these conditions are satisfied, then we definitely will have them. But even if they're not, we still could have them. We're just not guaranteed to have them. So one more thing I want to say before we actually get into examples here is now, if you think about what we were doing in the last couple of videos where we are classifying the critical points as local or max mins or saddle points, we don't really need to do that here. Like, we didn't in the single variable case either, but, just as a reminder of that, we just need to check each of the critical points and we need to check all the boundary points. It doesn't matter really if the critical points are local maxes or mins. We don't need to first say it's a local min and then it's a possibility for the global min, right? We can just ignore that part, especially That's going to be important because at places where the derivative doesn't exist, we didn't even have a way to classify them as local mins based on the second derivative. So we do not need to do the classification first. We can just look at the critical points and then look at the boundary points. Okay, so let's just jump into an example now. I think that's enough setup here. Okay. So let's look at f of x, y equaling x squared minus 2xy plus 4y squared minus 4x minus 2y plus 24 on D, which is what we normally call the domain, defined by x, y, such that x is between 0 and 4, inclusive, and y is between 0 and 2. Okay. So again, I don't think it's essential, but I do think it's helpful to draw the region that we're looking at first. Just a quick sketch. You'll see from the algebra, again, like it's not really essential, but I mean, I just think a picture always helps. So it's going to look like this rectangle right here, right? So basically we need to check every point along this line, 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 right? Including all those corners. So those, along with the critical points, will all be candidates for our global maxes and mins. Okay, so obviously we can't check every point because they're infinite. So we're going to have to use ideas like, well, the z is increasing on this axis and stuff like that. But we'll get to that. So we'll start just by looking at the critical points. That's kind of the easy part here. All right, so fx would be 2x minus 2y minus 4. Okay, and we're going to set that equal to 0. There's not going to be any point where the partial derivatives don't exist here because this is a nice continuous function. Kind of like a parabola, basically. So y now we have minus 2x plus 8y and then minus 2. So again, you can use whatever strategy you want to solve these systems of equations. I'll add these together just because we can see those two x terms will cancel out there pretty nicely, and we're going to get y equals 1. So that's a pretty painless one there. And then we'll sub that into the first equation there, and we'll get 2 minus 2y minus 4 equals 0. So we're going to get minus 2y equals 2. Or I'm sorry, I plugged that into the wrong variable. Right. So we're going to plug it in for y, not for x. 2x minus 2 minus 4 equals 0. So 2x equals 6. So x equals 3. So 3, 1 is going to be our critical point. So we want to evaluate the function at this point now. So f of 3, 1. So we have 1 squared. And I'm writing it. I know it's cut off, but I'm just trying to see the function here. 2 times 3 times 1 plus 4 times 1 squared minus 4 times 3 minus 2 times 1 plus 24. Okay. So 1 minus 6 plus 4 minus 12 minus 2 plus 24. Okay, so what do we got here? So that's minus 14 plus 24 is, we have 10. 14, 15 minus 6. Well, you got 9, it looks like. Let me just check here. That actually looks wrong. Let me see what I did here. Whoops, I did the very first number wrong here. All right, this should have been 3 squared because that was an x point. So this will be 9. So you can basically just add 8 to what we just had, which was 9. And that should give us 17, which is the right answer there. Okay. So we have that's our critical value, and now we need to check all of the boundary points. So the way we want to approach the boundary is kind of similar to how we were doing the limits, where we want to kind of substitute in one of the variables based on where we are in the line. So we're going to kind of break this up into 4 separate lines that we're going to look at here. Okay, so we're going to look at what are the values on this line, what are the values on this line, etc. So on this line right here, for example, we can see that right there, it's true that x is equal to 0 and y is between 0 and 2. Right? So if we let x be 0, then we can simplify this function a little bit. So we'll see what is this function when x is equal to 0, and then we'll just look at it between y is between 0 and 2. Okay, so x equaling 0 looks like it's going to leave us with 4y squared minus 2y plus 24. 4y squared minus 2y plus 24. So I'm going to break this up. I'm going to call these, let's call this L1, this L2, this L3, and this L4. So 4 different lines here that we're going to be checking, just to kind of organize this a little better. So here x is equal to 0 and y is between 0 and 2. Okay. So this is like f of 0y right here. So now we have a parabola, a single variable parabola, and we want to look at the max and mins of this between 0 and 2. So now we need to like find global max and mins in a single variable sense. Okay. So if we look at the derivative of this, let's just call this like g of y, just for notational purposes here. So g prime of y is equal to 8y minus 2 equals 0. So y is going to be 1/4 here. And then we also need the corners. So basically we have 3 candidates we're going to get out of this line. The corner f of 0, 0. Okay. And this is we've already plugged in x equals 0, so we can just plug the y point into here. So that's going to be 24. And I'm going to write all the candidates in red, just so that they're easier to see later when we're going back through it. Okay, 17. F of 0, 1/4. So we got to plug 1/4 into this, so it's going to be 4 times 1/16 minus 2 times 1/4 plus 24, and that's going to be, I have the answer here, so let's just write that down. Won't go through the fractions. And then the other corner is going to be f of 0, 2, right? So we're going to have 4 times 2 squared minus 2 times 2 plus 24. So that's 16 minus 4, so 12 plus 24. So that's going to be 36. Okay. And now we're not going to need to do all of the corners every time, right? There's only 4 corners total, so we just did 2 of them right here. So we're only going to have another 2 to do here. Okay. So let me I'm just going to change this so that it's more color coordinated here, just so it's easier to find things later. So L2 here, second line here, is going to be the line, what's that, y equals 2, and it's going to be where x is between 0 and 4. Okay. So y equals 2, x is between 0 and 4. Okay. So if we plug that in, so we want to plug in y equals 2 into this equation here. Okay, so that's going to leave us, I'm just going to write it here and then we'll copy it down. X squared minus 4x plus, is that 16? Minus 4x again, minus 4 plus 24. So we'll have x squared minus 8x, 12 plus 24 plus 36. Does that sound right? Yeah, that looks right. So we have f of x2 is equal to x squared minus 8x plus 36. Okay. And again, I'll just call this g of x. So this is going to, the derivative here will be 2x minus 8. So we have x equals 4. Okay. So our candidates, we already did one of the corners, right? We already did f of 0, 2 right here. Okay. So now we need f of 4, 2 as our new one. So plugging in 4 here, we'll have 16 minus 32 plus 36. So it's going to be, what, 20? And then that's going to be it, right? Because that's already our corner here, it looks like. So in this case, our critical point was right at the corner. Okay, so this must be an increasing function there. So now we'll go L3. So that one was the line x equals 4. Okay. Or this I was writing x equals 4, and then y is between 0 and 2. Okay. So that's this part right here. So x equals 4. So if x equals 4, we're going to have 16 minus 4y plus 4y squared minus 16, right? Minus 2y plus 24. Just gotta be really careful here. It's just so easy to, when you're doing a lot of steps like this, it's so easy to make arithmetic errors. Okay, so 4y squared minus 6y plus 24. 4y squared, I already forgot. Minus 6y plus 24. Okay. Let me make sure I didn't make any arithmetic error here. I did make an arithmetic error here. So this is what I mean here. We've got to be really careful. Really check these here. So this would be 16, and I put 2 in for this instead of 4. So that's minus 8y plus 4y squared minus 16 minus 2y plus 24. Okay, so 16, so that's 10y. So 4y squared minus 10y plus 24. Okay. So this is f of 4y. And we'll call that g of y here. So that g prime of y is equal to 8y minus 10. Equaling 0 means y is equal to 10/8 or 5/4. Okay. So f of 4, 5/4, which I'm supposed to do in red, is equal to 17.75. Okay. We do have another corner here. Right? 4, 0 would be the other corner that we have not done yet. So that's going to be 24. Okay. Which is the same as 0, 0. So we have all the corners. Now all we need is the last critical point, which is going to lie on L4. So that's on the line y equals 0. So that's going to be x squared minus 4x plus 24. X squared minus 4x plus 24. Okay, so that's f of, what was it, 0? Nope. x0. Okay, so this is L4, where y equals 0, and x is between 0 and 4 still. Okay, so call this g of x. So then g prime of x is equal to 2x minus 4 equals 0. So x is equal to 2. So that's our last point to check there. So f of 2, 0. It's going to be 4 minus 8 plus 24. So that's going to be 20. Okay, so total, we ended up with 8 candidates for global extrema here. We have 4 critical points, 1 from each line, and the 4 corners. Okay, so I did them all in red, of course, so that it's easier to identify here. So let's go through and find the smallest one first of all. Okay, smallest, 17 was in the one, right? So 17, I think it's the smallest one, right? There's 17.75 there. So this is the global minimum. Okay, so we have a global minimum at f of 3, 1, which equals 17. And then the global maximum, I think, is at 36 point. Okay. 20, 24, 17.75, 20. So yep, it looks like this 36, which is at 0, 2. Okay. All right. So as you can see, it can be quite a grind getting into this point. In the next video, we'll look at one which is a circular region, which is actually, I think it's a bit more complicated conceptually, but the math is a little bit shorter because we don't have all those, we don't have to break it up into 4 different parts, right? Like here we did. It's just one continuous line. So it's a little bit harder, but it's a little bit shorter as well. But yeah, this can be quite a grind. So just be careful, you know, using the calculator where you can to avoid making those arithmetic errors, and just being really careful not to like mix up the x or the y's at certain points. And again, drawing the picture. So you technically don't need the picture here. You could just divide this out, but I think the picture makes it a lot easier to handle. So then you can see exactly like what y is on certain points, or what x is, or whatever it is that you need.